invitation, and thanks for being here. And I also want to thank you organizers for making these talks publicly available, especially during these times. And it's a very good service to us, and thank you. All right, so let's start. So I will be presenting a collection of work based on collaboration with a large group of people, as you can see. But I would most of all, I would like to highlight work of Seung-Cheng Liu, who is my PhD student, and he's just brilliant. And he's also graduating this year, so you may want to keep an eye on his application. Bulk of the work I will present is with him, and then there's work with Tim Shea and John McGreevy, Daniel Banzine. I couldn't find his photo, and then Kai-Shin Wu, Jiamin Zheng, and Yingzhe Cao. I've been very fortunate to have these great collaborators. So let's start. Yeah, and please, I don't know, feel free to ask any questions along the way, and there'll be also time at the end. So it's not working. The next slide. Okay, it's working now. Yeah. So the very broad. So some of it maybe has some overlap with my past talk I gave at UQM, but there'll be a fair bit of new stuff near the in the later part of the talk. So let me start with very broad motivation. Does quantum mechanics matter at non-zero temperature? And by that I really mean universal properties at non-zero temperature. So let's take one example to maybe set up this question. So consider, for example, the question of topological order at finite temperature. As you know, that topological order is a well-defined concept, for example, in the ground state, and defining it at non-zero temperature is a slightly tricky topic. But it's for example, to be able to define topological order, you would want to be able to define braiding of particles, so braiding of anyons. So if you can do that, then perhaps it's a reasonable kind of guess that topological order is well defined. So let's consider in that spirit three-dimensional Toric code. As you know, that 3D Toric code has two kind of excitations, a charge and a magnetic loop, and they have mutual pi statistics when you take charge around inside a loop and come back. So at zero temperature, you can implement this braiding without any issue. We know that. You can just do this. But what about at non-zero temperature? At non-zero temperature, you encounter what is called quasiparticle poisoning. So because charges cost on the order of an energy, there's a finite density of these charges at any non-zero temperature, which makes braiding hard to define. So if you, for example, because the charges exist, so many of them, and they're moving around, so when you try to take a loop around the test charge, your anionic phase, this topological Barry phase, gets polluted because of other non-test charges. And this phenomena in the context of topological quantum computing is called quasi-particle poisoning. And this is supposed to be the reason that topological order does not work at finite temperature in 3 dimensions, or for that matter, 2 dimensions. So in this sense, the truly quantum nature of this topological phase is lost at non-zero temperature.
Can I ask a question?
Sure.
So what words would you use to describe the low temperature phase of this 3D Toric?
I will call it a classical topological phase.
A classical topological phase?
Yeah, because it can be mapped to a classical gauge theory, which is very well defined, and has, for example, to capture the non-local order in that, you can look at the von Neumann entropy, and its subleading term captures it. But if you look at any true quantum entanglement measure, it will be 0 in this low temperature phase.
So it's classical topological order. That's what you're saying, as opposed to
that's all. Exactly.
All
so,
right.
So I want to make a distinction between quantum and classical topological order.
All right. Yeah, maybe it's good to emphasize that.
Right. So the 3D, I Ising-Gauge theory has a low temperature phase which is separated from high temperature phase by a phase transition, and actually I did not realize till 2008 or so that this low temperature phase did not have any quantum topological order, and I learned it from Benny Yoshida. He did a lot of work in that, and he was a student at MIT. In fact, he gave a talk in our ship year.
Tarun,
anyway.
related question, may I ask that, in terms of kind of zero temperature,
Right.
we can talk about, say, topological order, but in this sense, you can say that non-zero temperature, it's where you are going to excited states, right? So you're considering not just a ground state, you're considering excitation. So I don't know, quantum or classical, does this notion of topological order make sense for, classification of excited states as well? Because it's instead of temperature,
right? That's one of the broad aims here. And that's what the talk is about broadly. If I give you some Gibbs state, for example, how to think about topological order. So that's the talk is mostly, So let's, exactly. So we will see more about it. So a related motivation is how to distinguish quantum from classical phase transitions. Your general, at least if I open a textbook on phase transitions, the general argument goes when you're at non-zero temperature, the thermal direction is finite of extent beta. So you have, basically, so then there's no extra dimension, and you can think of that transition as essentially classical at non-zero temperature. For example, if I take this transfer-serializing model, actually, is my arrow visible? This arrow, which I'm moving around.
Yeah.
Thank you. So this whole line is in the universality class of classical 2D Ising class, which is same as when transfer field is 0, right? So that's clearly classical when transfer field is 0, and this whole line is in the same class. So that's a classical transition despite the model being quantum, and this doesn't surprise us because the thermal direction is finite. So this argument about mapping a partition function to the same dimension as a space dimension seems convincing, but it can't be clearly a fully correct argument, because we know examples where this breaks down, and I will talk about that. And if you take a four space dimension Toric code, then quantum topological order survives finite temperature. So you do have non-trivial quantum entanglement at non-zero temperature. So the finite temperature transition should be truly thought of as a quantum phase transition. Even if it is first order, it doesn't matter. It's first order, second order, but the main thing is you lose quantum topological order. So more generally, just partition function should not be enough to determine something is quantum or classical. That's pretty dramatic statement, right? I mean, you have to know a bit more about eigenstates and structure of entanglement to say some statement. So I think this using this partition function argument, I don't find it satisfying, and that was another motivation here. So if finite temperature transition is really classical, then a true measure of quantum entanglement must be short-ranged, despite a diverging correlation length. So that's a very big challenge, right? I'm asking you to give me some quantity which has correlation functions which decay exponentially even at the critical point, at finite temperature critical point, and that will be one of the aims here. So more practically speaking, if finite temperature correlation length is small, people have argued that the Gibbs state can be prepared with a small depth channel. So there's been a lot of work on that. But here I'm saying that there's a possibility that finite temperature correlation length may be infinite. Even then, the quantum correlation length is finite, which means that you might be able to still prepare such a highly correlated state, which has only classical correlations at all length scales, using short depth quantum channel. At least that's one of the motivation for this way of thinking, and I suspect it can be done. And maybe I won't get into algorithm right now, but some of it has been developed by Steve White and Miles. So that's an interesting statement, because these proofs which people have used recently do not even get into it. They always work when actual correlation length, physical correlation length is
sorry,
is
Tarun, I'm sorry to disturb you. Maybe it's out of your line, but can you just one word? What does it mean? Small depth channel. I've never seen this before. So it's some jargon.
So you're familiar with finite depth unitary. or should I define that first? So the idea is that you can start from a product state and then apply, think of the circuit model where you have an initial state, which has several legs coming out, and then you have this brick wall circuit, and the depth of that circuit, length is the space dimension, depth is how many you apply. So that's the depth of a unit tree. Now channel is a generalization of that to density matrices which are mixed. So if it's not a pure state, but a mixed state, then instead of unit trees, you're allowed to apply more general objects called quantum channels, which I wish there was a blackboard, but it's essentially look like, so the unit tree looks like U, rho, U dagger, right? Rho goes to U, rho, U dagger. A channel involves a set of things called cross operators which are denoted by V alpha, V subscript alpha, and rho goes to V alpha, rho, V dagger alpha, sum over all alpha, with the condition that V alpha, V dagger alpha, sum over all alpha is identity.
Right, and they're local in some sense.
Exactly. Sorry, that was very important to mention. I meant small depth local.
Right. Thank you.
Yeah, I wish there's a way to set up my iPad to make it a blackboard, but I think it will, going back and forth may spend too much time. So let me try to use those words. If things get very complicated, I will try to do that. Thank you for the questions. So another related motivation, which is again about mixed states and essentially open quantum systems, is that when a system does not thermalize, our expectation is that the entanglement between two subsystems A and B must be large. Why do I say that? If the system, so the idea is consider a tripartite system A, B, and C, and now look at a density matrix over A union B. So I traced out region C. Look at a density matrix of rho of AB. If the system has not thermalized despite tracing out C, so the idea is that C is acting as C is trying to act as a heat bath, but it's failing to do so. If that happens, the entanglement between C and A union B is small. That's what it means, that it did not thermalize A union B. Because of monogamy of entanglement, I mean, something has to, and A has to be entangled with something. If A is unable to entangle very well with C, which was trying to act as a heat bath and failed, A must entangle with B then a lot. And so this may be a way to understand distinction between systems which thermalize and don't thermalize by understanding mixed state entanglement of the density matrix rho AB. So for example, take this simple trivial example, consider a random Haar state. As you know, it has this page curve that entanglement entropy as of, so I integrate out C, look at a density matrix. So S here, S of region AB, A union B. So it goes up and then it goes down. So in the regime where it is going up, it's behaving like a thermal entropy because it's proportional to volume of AB. So it means region C is acting as a good heat bath. And when it's going down, that's a very strange system. You are increasing the size of region A union B, but its entanglement is decreasing. That's a very strange system. That's not a thermal behavior at all. And you can check that easily check that the mutual information between A and B in this thermal region is basically 0, which means that A and B are not entangled much. But in the other region where things are non-thermal, A and B are highly entangled. In fact, it's volume law. But mutual information is not a good quantity for a variety of reasons, which I will discuss later. Mutual information is not a true measure of quantum correlation. It gets polluted by classical correlations. So we would like something which is only sensitive to quantum correlations, because mutual information can be non-zero even in a fully classical system. For example, just take a thermal system, it has mutual information. I mean, so just take a purely classical model, it will have large mutual information typically. So we would like some measure of quantum entanglement to understand this fact and perhaps exploit it to understand distinction between, for example, many body localized systems or integrable systems, maybe system which has scarce states and so on. So these are the two motivations. So both of these things kind of push us to understand mixed state entanglement. So the zeroth order question you ask, similar to the case of pure states, when is a mixed state separable or unentangled? These are two words which I will use interchangeably. And for example, for a pure state, we know a state is unentangled if it's a product state between two parts. And thinking of a bipartite entanglement, if psi can be written as psi of A tensor psi of A bar, that's a separable state for a pure state. So what's the generalization of that to mixed state? So that was maybe not that hard to see that this is the correct answer. If you can write down density matrix rho, a mixed density matrix rho as a sum of separable states. And there's an argument that you can think of rho IA tensor rho IB, each of these elements with index I actually as a pure state. So you can map that to, if you prefer doing that way, rho IA tensor rho IB can be thought of as a projector onto some pure state. So that's that can always be done by, I can't get into the argument, but the idea is if you can represent a mixed state as an ensemble of pure states, each of which is a product state, then as you can convince yourself, then there are no Bell-like inequality violations between region A and B, because whole idea of mixed state is you're given ensemble of pure state, that's a mixed state. And if you can prepare each of those elements of the ensemble without any quantum communication between parties A and B, just by classical communication, you can prepare these things, then clearly it's an unentangled state. That's a very good definition. So that's how people think about it, and it's pretty reasonable. So let's take an example. Consider a state which is with probability P. I prepare a EPR state, maximally entangled for just it's a 2-qubit state, and with probability 1 minus P, I prepare an identity state. So you can ask, what happens? When is it separable or non-separable? When equivalently, are there any Bell-like inequalities which are violated? So then I will call it non-separable. So surprisingly, answer there is a transition at 1/3. I mean, intuition fails here. It's not very obvious. You have to really think about it and do some calculation. But so mixed state entanglement is not the most intuitive thing, but it's very useful for all kinds of purposes. So that's one of the motivations. So what are the many body analogs of such transitions? You can ask. So a more physical definition, because we are working with many body systems where there's always some short range entanglement, let me propose a more physical definition. Maybe people don't do it, but I find it very useful. If you can represent a mixed state as an ensemble of pure states, each of which is short range entangled, that doesn't have topological order or doesn't have long range correlations, think of some basically like a short range correlated paramagnet without anything funny, then I will call rho a short range entangled mixed state. So let's dive into one example right away. So consider 2D Toric code at finite temperature. Rho is E to minus beta h. These are two, all of you, I hope, familiar with Toric code. So, so if you write it in eigenbasis, it looks, it's hard to tell it's separable or not. Each of these eigenstates of Toric code have topological order. These are pure state which have, you can calculate topological entanglement entropy. All of them have topological order. So it's not obvious whether rho is short range entangled. So here's an interesting trick you can do. So insert a set of, insert identity matrix in between, and choose this M to be set of all product states in the X basis. Then you can show that in this new basis, each of these phi M's are actually not topologically ordered at any non-zero temperature T. So this, I should actually mention this. This construction shows up in DMRG, not for Toric code or anything related, but people use such an idea of putting set of complete product states. It goes by the idea of minimally entangled typical thermal states. So I should mention this. This is Miles and Steve White's thing, which we use for doing DMRG, but it turns out this idea was also useful for us for showing that 2D Toric code can be written as a sum of short range entangled states. So it's a very straightforward calculation, but it's very enlightening. So then you can generalize this to any dimension, 2, 3, 4, you can go higher if you want, but the result is if you think of Toric code as a two terms, one is only X, sorry, one is only Z.
Sorry, Tarun.
Sorry.
Tarun,
yes.
Yeah, can you repeat the logic here? Why so what led to the conclusion that it's not
topologically ordered
Yeah,
state.
it's not topologically ordered.
Because the loops which are large are suppressed by exponentially minus area.
Oh,
the
okay,
weight of a
fine.
yeah, and you can
So
calculate
there's no
for
large
example
loop,
Wilson.
basically. You're saying there's no large loop. Okay.
Exactly, and you can also calculate Wilson loop and show that because it's pure gauge theory. So you can calculate with respect to this pure, and you can much more than that. You can find an exactly soluble Hamiltonian for which each of these states phi m is a ground state. And there's a construction in the appendix of a paper. It's a bit involved, so I can't get into it, and you can show from there also. So there's several ways. So Toric code is what is called a CSS code, which is one term is only X, other is only Z. And this argument works for all such CSS codes, including house code, fracton models, any of them. And you can show they don't have topological order at any finite temperature, including these other models. But looking to just Toric code, you can show that you can find such separable representation when temperature is bigger than minimum of T at TB, where T and TB are tabulated here. So you see that in 2D, this both the minimum of T at TB is 0 because L goes to infinity. This is in 3D also minimum is 0, and 4D it is order 1. It does so at least we have shown that 2D and 3D it's separable. It's possible we did not work hard enough to show that 4D is also separable. Who knows? I mean, we choose some specific, as long as you can find such presentation, you can. It's a if statement. I mean, okay. I mean, as long as you can find it, there are infinite such decompositions. So who knows whether we fail to find such a decomposition in 4D? But at least 2D and 3D we showed. Now what about 4D? So this requires to find some actual measure of entanglement rather than just this. I mean, this such construction. So you need to find some notion of non-separability. All right. So so the von Neumann entropy I already mentioned is not a good measure. Yes.
Quick question.
Yes.
If you go back, so you have this sum over m, right?
Right.
And I'm wondering, this is an infinite sum.
Right.
Like, can things hide in some very high m terms? Like you get some very, very highly excited thing somewhere high up in the spectrum, I don't know.
But the way we are working is we are working with a finite system, and all 2 to the power L number of states we know we have exact construction for all of them for a finite size system. We are never even taking I mean, we are working with finite system. Each of phi m we know exactly.
So you require that really for all.
Yeah.
Strict.
It's not for, okay. Let me be more. So there is something called entanglement of formation, which involves averaging over all. For example, take each of these phi m's, calculates bipartite entanglement entropy. Because a pure state, von Neumann entropy is a good measure. So you can define Pm S A of phi m, sum over all m, as the average entanglement of this decomposition. Now you minimize over all such decompositions. That is called entanglement of formation. So that averaging gets rid of some very rare states. I mean, depending on how it works out, and that's a very good measure of entanglement. It has been argued because of various reasons. So there's a way to deal with this question about how much do rare states matter or don't matter if you do this averaging, which enters the definition of entanglement of formation. And the reason that's a good quantity is because people have understood it in terms of operational definition, whether you can generate qubits out of such state or not. So you can answer that also, but here we do not have to.
I see. So these statements you think also hold if you perturb the Toric code a little bit.
That's what our expectation is, and that's why we wanted. We would like someone to do some actual numerics. We could not find anyone who's willing to it so far, but we wanted to stick with solvable models. So it'll be very nice to do that, and maybe Yingzhe might be interested. I think he was interested. So anyway, so the von Neumann entropy is not a good measure. I already argued. If we take a Gibbs state of a classical Hamiltonian, of course it has volume law von Neumann entropy. So clearly it's a bad quantity. But just to even see more. People have been using it for some time, so it's good to emphasize that what can go wrong. So this is, for example, take the 2D Toric code and send one of the terms to infinity first, and then take L to infinity. Let's say lambda b to infinity. One of them doesn't matter. It's dual. So you will find that the topological part of von Neumann entropy, which is a subleading term, which can be obtained by Kitaev-Preskal subtraction schemes, remain half log 2 up till infinite temperature, because you have suppressed one kind of charge. So it's not surprising, and it shows up as a numerical effect when you look at some of these models, like this Balance Fisher-Gervin model, you will find a half log 2 plateau here it is log 2 because they are defining 2 gamma anyway. So it's, but up till some length, up till some temperature scale, which is crossover scale, which is lambda, in a real numerics, it will be lambda b over log of L, because log of L can't be very large in real numerics. So it basically looks like an order 1 number, lambda b divided by log L. So that you will see a plateau there. But my point is, this is a purely classical thing. It's nothing quantum about it, and it should not be confused with a true topological quantum entanglement entropy, whatever that, I mean. Entanglement is a word reserved for quantum mechanics. So it should not be called topological entanglement entropy, this half log 2. So now you can do the same thing in 3D. You will find then, in fact, order 1 temperature, lambda b. In 3D, you don't have to even take any limits. There's a half log 2 left over. And this is known from old work by Castellano and Chamon. And of course, they were not saying at all that it's quantum or anything. They were just, they called it classical, I think, as far as I understood. So that's fine. And so you see that quantum entropy can be misleading. So that's why, so we use this quantity called entanglement negativity, which is a true measure of mixed state entanglement, and it's always 0 for separable states. It can be 0 also for non-separable states. So colloquially speaking, it throws away all classical correlations, which is good. I don't want to be confused with classical correlations, but it sometimes also throws away some quantum correlations. And based on examples, we know the quantum correlations which are thrown away are typically short distance. So, but okay, we don't fully know, but anyway, here I'm just focusing on measure which throws away all classical correlations. So that's good enough for what I want to do. And it has some nice physical meaning in terms of rate of conversion of states to EPR states. So, and there's a lot of work, and in fact, so I can't cite, this is not clearly exhaustive list, and there's a lot of work on this by many people in various contexts. So one of the most interesting result is its area law of entanglement negativity. So the thermal states, if you look at, so take a Gibbs state, divide into 2 parts, A and B, and look at actually maybe I didn't define very well. So what I'm doing here is I'm doing what is called a partial transpose over region B. So it's some operation. I wish again I had a blackboard. I think maybe I missed that slide. Sorry, but we don't need the definition actually, which is kind of strange thing to say. But I think it's a short talk, so I really can't get into details. But there is some quantity you can define using partial transpose over region B and take 1 norm of that. So so the nicest thing about this is it's a area law. So it already throws away all this classical correlation which were making us worry. That's a good start for any quantity which claims to be a good measure of quantum entanglement. And the intuition is you're trying to understand entanglement between A and B in a thermal state. So you can purify the system to get C, which is now is a pure state. To purify, you need a large N of C. And because large N of C will entangle very strongly with A and B, so the actual entanglement between A and B should be small. So that's when we think about why it's area law. So you can decompose now negativity because it's area law. You can you can play similar tricks as you play with von Neumann entropy of pure states. You can decompose into local and non-local parts and do this idea of curvature expansion, which long ago we worked with Ari and Ashwin. And all of those tricks go through, and you can do something even using similar idea. You can do Kitaev-Preskel subtraction scheme to extract a subleading term. So we'll do that here. Can everyone hear me? I think people disappeared, or I don't know.
No, we can hear you.
Okay, I don't know. Somehow the list of people, I don't know. Maybe it's my computer. But so then so the subleading term we are interested in of this, which we call topological negativity, and our understanding is that's what captures this non-local topological order. So so let's do that. So this is the result. You'll find that it vanishes. Topological negativity vanishes minimum T star A T star B, where I tabulated these T star A T star B, and these are precise. Is the same result as we earlier obtained heuristically using this decomposition of a mixed state into into pure state. So the minimum temperature quoted there was the actually correct temperature. So this temperature remains order 1 in 4 dimensions, and contrasts it with topological contribution of the von Neumann entropy. That is at maximum rather than minimum. So that's a drastic difference. That's why in 3D and 4 in 3D you get a spurious, not spurious, whatever. You get a result that it remains non-zero up till some temperature. So it should not take it as a measure of any quantum entanglement. So so I can go through these examples. I feel like I'm really running behind in time, but let me try. So if you are for example, in 2D, you get this result, topological part of von Neumann entropy remains half log 2 when you take lambda bit infinity, but the other one vanishes immediately. So it really knows about the braiding, actually. In fact, when we calculate it, braiding shows up somewhere. So that's a technical detail, but I can't explain right now. But it's sensitive to braiding of quasiparticle. It knows about quasiparticle poisoning, this topological negativity. So you can calculate it analytically in terms of some interesting hypergeometric function, and you can see how it interpolates between ground state and finite temperature. So when you take thermodynamic limit first, L going to infinity first, and then take temperature to 0, then you get log 2. But if you take temperature to, anyway, I mean, if you, I said it wrong way. So if you take L to infinity first, then take T to 0, then it's a thermal state, then you get 0. But if you take temperature to 0 first, and then take L to infinity on the ground state, then you get log 2. You can do similar thing in 3D Toric code. If you first suppress the placket excitations, so let's take lambda b to infinity and take lambda a to order 1, then you have point-like charges. So what do you expect? You have point-like charges, they will cause quasi-particle poisoning. So you expect topological part to be 0, and that's what you find. And in fact, you can do analytically this whole thing and find the exactly same result this one. But do the other limit now. First send lambda a to infinity. So suppress all the point-like charges and keep lambda b to be order 1. So that's an interesting limit. It's a fine-tuned limit, but you file non-zero topological order at non-zero quantum topological order at non-zero temperature, because you have suppressed the point-like charges completely. So quasi-particle poisoning cannot occur because things are not moving. So in this picture, like you can do it because of that. I mean, I'm not taking lambda b to infinity, otherwise they won't even move, but lambda b is large enough, there's some crossover. So this is a way to mimic 4D Toric code in 3D. And you can do the 4D Toric code also, and you'll find non-zero number, which is 2 log 2. And factor of 2 is important. It is related to the fact that it has membrane operators and so on. And anyway, so this is the result. So there's, yes?
This is the 4D Toric code which has only loop excitations, isn't it?
Yeah, 2, 2. Yeah.
Okay. Mm-hmm.
Sorry. Yeah. So the 3, 1 does not have this. So this is the result. There exists some finite temperature quantum phase transition in the 4D Toric code, but not in 2D and 3D. Unless in 3D it can exist if you take this limit, and that's why numeric should be first done there. I think someone should do that. In 3D Toric code, take that limit. It's not too hard, but I couldn't do it myself so far. But anyway, it'll be nice. So so let's see how we are doing on time. So the second part, which is about distinguishing quantum classical phase, is closely related. So let me try to summarize it, at least how what are the main results. It's related to this first part. So we want to understand, earlier I kind of asked this question, if you could find a true measure of quantum entanglement, it should not see this transition really in thermodynamic limit. Maybe at least it should not have any power law correlations at this critical point. Have we found such a thing based on negativity? So let's see. So the first thing we did was took a exactly solvable model, which is a funny looking model. It mimics transfer serializing model at finite temperature in 2D, but it's a stabilizer model, so you can solve it. So we wanted a model which has non-zero negativity. So these are the conditions. We want a model which is exactly soluble, has non-zero negativity at finite temperature. It should not be identically 0 or something like, it can't be just a classical model. And it should have a phase transition at finite temperature. So putting all those conditions, this was the simplest thing we came up with. And so our naive guess was negativity will be non-singular across TC, at least, okay. That was, we were guessing long ago, but, and this was also kind of hypothesized in this paper by Sherman, Devko, Matt Hastings, and Rajiv Singh, that they were thinking negativity will be non-singular across transition. So we calculated it, and it's singular.
Tarun, can I just ask? So this model, so you say it mimics the Ising models. It's a symmetry? Does it have a symmetry breaking phase in there?
It has a symmetry breaking finite temperature transition. Yeah.
Okay.
Yeah.
The local order parameter. All right. Thank you.
And it's a local model, as you can see itself. And you can consider other models, which are spherical models, which are also doable. But we wanted to separate between shorter entanglement and longer entanglement. That's hard to define when you have all-to-all interactions. So that's why we found this. So you can't solve it like all the things exactly, but you can do small clusters analytically. And that was good enough for what we wanted to show. So if you take a small cluster, like few sites, and look at its negativity with rest of it, find singularities. And the singularities in negativity are related to the leading singularity of the critical behavior, which is, you find the operator which is symmetric and has the smallest scaling dimension, its energy density. So that's what determines the singularity of negativity. So what's going on? So this is a main picture, that of course there is short range entanglement, which is, so the entanglement is even at a critical point, the quantum entanglement is only up to some short distances, which is quantum correlation, and which is basically like beta. It's not physical correlation, and which is like 1/t minus dc. So negativity is a function of expectation value operators in this small region, which is close to boundary. And expectation value of local operators are of course singular, like energy density is singular across transitions. So it gets picked up by negativity. So it's not very surprising that negativity is singular at all. So the main thing you have to do is to subtract off this short distance singularity. So write negativity as negativity of local versus non-local regions, and do the ABC subtraction, Kitay-Preskel kind of thing. So to do that, we needed to find a model which is even more easier to solve. This model requires a Monte Carlo. We didn't want to do that. We can do it, but let's look at something even simpler. So consider this Ising model within Gaussian approximation. So you can describe high temperature phase in a simple way, like the FIFO term, at low temperature, you just expand around the new minima, and just the standard thing. So let's look at this. It's a soluble model because it's Gaussian, but it has singularities because of the way, from the Landau theory singularities, mean field singularities. So if you look at Von Neumann entropy, it's clearly singular across transition. It has log L singularity, which is well known from this Fisher, Gelfand, Perman, all this old stuff. So it has log L singularity because it's a Gaussian model. And similarly, a mutual information will also have log L singularity at the critical point. Next answer, areal coefficient of negativity. You will find that's also singular, as expected based on previous thing I mentioned, that short distance, there's a short distance, areal of negativity is singular. That get picked up because of the energy density, and the exponents match what we expected from energy density and so on. So far, nothing kind of maybe super surprising, but now we started doing ABC subtraction to look at the long distance part of this negativity, and it decays exponentially. So you can do scaling and all that, and you can see it's basically invisible. After system size become 50, it decays so fast, even at the critical point. So this is one quantity we found, which decays exponentially even at the critical point. And that's what we were after, and it seems to work. So again, this is a picture that is a quantum so the system has two different length scale, what we call quantum correlation length, or which qubits are correlated, and that's like beta. And there's a larger length scale in this case, which is diverges, which is some 1/t minus dc to some exponent.
Sorry, just to make sure. So if I just calculate the von Neumann entanglement entropy, it's going to have singularity, even if you do this kind of ABC?
Of course, because you can't cancel out log. Mm-hmm. Logs are impossible to cancel out after ABC subtraction, because it depends on, how will you cancel out log ever? Mm-hmm. So it's the same thing which shows up. So in fact, this singularity so if you take, for example, 3D Ising, 2 plus 1D translated Ising model at finite temperature. So Roger Malko and collaborators looked at its mutual information at finite temperature, and it is singular, of course. So mutual information is not, and of course, in old days, people were thinking mutual information as a measure of some entanglement, but of course, it's misleading because mutual information gets polluted by classical correlations, and it picks up all the singularities. In fact, that's how people detect transition in that case in Roger Malko's numerics. I'm not saying he was misled. I'm just saying some other people have talked about mutual information and they as a measure of entanglement, that it's not. Is that clear?
Oh, sure.
Yeah. So this quantum correlation is infinite in for the Toric code. So that's why it's a very interesting case. So so more things you can do by looking at the so the way negativity came was from taking a one norm of a partial transpose. So you can ask, what about those partial? So the partial transpose has some eigenvectors and eigenvalues. Negativity only was sensitive to the eigen values, not eigenvectors. So what about eigenvectors? Do they have some interesting information? And the answer is yes. So look at only those eigenvectors which contribute to negativity, which have negative eigenvalues. So again, if you don't know definition of negativity, I'm sorry, I went too fast, but the idea is take partial transpose, look at its eigenvalues, eigenvalues which are negative contribute to negativity. That's why the name came from. So if you look at eigenvalues which contribute to negativity in this free model, you will find those eigenvectors have correlation functions which are, I mean, those eigenvectors are basically localized close to the boundary, and the other one look like plane wave. That's a pretty interesting thing, because to me at least, this was the most interesting thing in the whole thing, because it's, I don't know, something about it. It just that even these eigenvectors are have a lot of information, which people sometimes, I mean, I've never seen people actually using them for anything, but so you can see the area law from it. You can even extract the quantum correlation length from this. So anyway, so now let's look at the more interesting model, which is transition model. So we can't calculate negativity for this. That's too hard. But you can calculate what is called a Rayleigh negativity, which is a version of negativity. So what we did first was to look at this Rayleigh negativity for solvable models, and found it has same behavior as negativity. It has all the things I mentioned so far works for this, at least for solvable models. That gives us some confidence that it works for even a non-solvable model. At least it's some evidence. So we looked at it in the transition model. This is work with Ying Zhe and Kai Shin and Chiamin Chung. And we found that the area law part of negativity again is singular as we expected, and all the scaling works out. You can do the scaling fit, and even if you don't understand this curve, but the main summary of this curve of this plots is that we are looking at area law coefficient of negativity, and it has same singularity as we expected for energy density. So here we're looking derivative of area law. That's easier to measure, dr3/dt, and it matches the singularity of the specific heat. Now the main part is, what about the ABC subtracted negativity? I mean, we are taking combination of quantities, all of which are singular, right? And we are doing numeric. So it's not very easy to see things will just cancel out, because each of those terms are singular in this ABC subtraction of quasiparticles. So we did that, and this is what the result looks like. It's basically 0. So this is gamma, which is combination of, we use actually Levin-Venn rather than quasiparticle. So, and it's within error bars, it's just 0. And all the terms we are combining, they are all order 1. So that's pretty interesting. And somehow it vanishing. So that was very interesting. So any questions here? So we are done with the first part of the talk, and the last part is I'm about to begin, but if there are any questions here. So seems like not. So let me come to the new part. So all the stuff I mentioned may be okay. At least you have heard bits and parts maybe somewhere before, right? Or you can find it online. At least this part is new and maybe more excited because recent. So I earlier mentioned this motivation. When the systems don't thermalize, we expect that the entanglement between A and B to be large. So if C is not a good heat bath, then maybe A and B are highly entangled. So this is the main result. So if you take again, I'm considering a tripartite state A, B, C, and I integrate out C to get reduced density matrix of A union B, and look at the, so take rho AB, do partial transpose over, let's say B, to get entanglement between A and B in this mixed state. So when you have a non-integrable system, there's a phase transition from area law to volume law at 1/2 for eigenstates for this negativity. There's a very similar transition in the long time evolved states. So if you take some product state, evolve it, then trace over C at long times and get rho AB and so on. And F star is some order 1 number, which we suspect to be half, but okay, we couldn't prove it. But anyway, maybe it's not, I mean, it's order 1 that we can show. So for integrable systems, it's always volume law. So A and B are highly entangled always, which is again the intuition we had that if C is not acting as a heat bath because it's an integrable system, we expected A and B to be highly entangled, and they're always highly entangled for integrable systems. Similarly, so the long time evolved states and are similar for integrable systems. For many body localized, we already know eigenstates, how they behave. They're always area law, so that's old stuff. But the interesting thing is this long time evolved state of MBL is interesting, right? Because that goes to volume law, as you know. Entanglement grows log T, and it becomes, so that state is not very well understood. And what we found, at least numerically, it also has volume law negativity, which shows that it's a highly kind of a glassy state where C is not acting as a heat bath, but A and B are highly entangled. So it's a very interesting state, actually. It's actually a more interesting state, most interesting in all of this phase diagram, this MBL long time state. Anyway, so let's try to see some numerics. So that takes a volume, first look at integrable system, which I claimed it has volume law negativity always after tracing out region C, irrespective of how big C is. So, so this is LAB over L. You can see that it's always volume law. And contrast this with chaotic system. In the chaotic system, you can see that how things look very shallow up till 1/2, then they grow. In the integrable system, they don't look as shallow and they keep growing. So this is the difference between integrable and chaotic states. So this is basically the derivation of the integrable system, why it has this volume law negativity irrespective of size of region C. So we use this very useful picture called quasiparticle picture of Cardi and Calabrese to understand this. So the idea is this: you divide system into A, B, C. A is the red part, including the irrespective whether it's dotted or not. All of red is A, all of B, all of blue is B, and all of green is C. So the way entanglement is generated between A and B is by shared quasiparticles. So one of them has to be in A, other has to be in B. So the number of quasiparticles A and B can share is proportional to region length of A and B. Let's take to be equal size, LAB over, say, half. And the fraction of time these quasiparticles can entangle is a fraction of time they spend time, one is in A and other in B. So a simple counting, and if you can look at the paper, there's a more detailed calculation which gets even the prefactors, all the things. You will find basically multiply this fraction of time times the number of quasiparticles that can be shared. That will be volume law. So people have looked at negativity before for various systems, but they never looked at this limit. And other limits you just find 0 generally at long times. So you can't tell a distinction between chaotic system and at least in long time limit. But this way you can tell the difference. It's volume law at long times. So you really have to scale A and B with total volumes. So the quasiparticle picture breaks down in chaotic systems, like the integrable system. If you do a local quench, like this lightning is a quench, things just propagate. In a chaotic system, things just keep breaking apart into smaller and smaller pieces. So we don't expect this the picture to hold. So this shows up in chaotic system. I earlier mentioned there is a transition from area to volume law at 1/2 for eigenstates. So this is numerics. So can we make some progress, analytical progress on this? And this is challenging because it's a chaotic system, but eigenstate thermalization is useful to understand these things. So just to even emphasize a bit more, to distinguish various systems, integrable versus chaotic versus many body localized, this is a useful diagnosis. You can see the result for many body localized also. It's always volume law. In fact, it looks much more volume than anything else, the many body localized one. And the chaotic ones is we can show it's area law at small LAB over L. So anyway, so this is the diagnosis. So what is the understanding of the area law? We call it subsystem negativity because we're integrating out C. What is the understanding of area law of this quantity for chaotic eigenstate when VAB is less than VC? That is, VAB is less than 1/2 of the total system. So the idea is to write Hamilton HAB plus HC plus some boundary term. HABC is just some boundary term as a sum of local terms. So when VAB is much less than C, then we know ETH just the standard ETH, where reduced density matrix of AB is just thermal. And for thermal states, as this work by Sherman and Dave Cole Hastings Singh argued that thermal states have area law negativity. So that part is obvious, but that's not what we are interested in. We are not interested in this small volume limit, which is just the origin essentially here in this plot. We're interested in the whole regime when it's order 1 but less than 1/2. So that requires much more work. So then we use this very nice work by Hong Liu and collaborators, where we write down dense. So it is it's based on this idea of subsystem ETH, which kind of conjectures and give a lot of evidence for it. This statement that the reduced density matrix of region AB, when VAB is less than BC, takes a very specific form. It's essentially like saying that all states which are allowed are equally likely. It's like ergodicity essentially. So even if you don't understand it, just doing the usual notion of ergodicity. And then, so using this form and I don't know, a series of triangular inequalities, which is what the only inequality there is. So then you just prove this result that a negativity is area law. There's some order one numbers, and J is basically the norm of local Hamiltonian, and the partial VAB is the boundary size. So there's some work involved. I can't get into it. It's fairly involved proof, but you can do it analytically. So what about volume negativity in a chaotic system when VAB is bigger than VC? Like we are saying that when VAB is bigger than VC, it's volume law. There's a transition at 1/2. And that's much harder to access because entanglement Hamiltonian is highly non-local in this regime. So that suggests that it will be volume law. But to make progress, we use this what we call ergodic, tripartite ergodic ansatz for eigenstates of chaotic Hamiltonian. It's based on this many-body Barry conjecture of Barry and Shrednicki. It's basically you superpose all kind of states. All of them are made of eigenstates of HA, HB, and HC, and superpose them with some random complex numbers with some energy constraint. So which is kind of very much like Barry's conjecture for billiard balls, and this is how actually Shrednicki started thinking about ETH. So we're using that. For that, we can't calculate negativity, but we can calculate Rayleigh negativity. It remains an open question how to calculate negativity for this. So we look at Rayleigh negativity. It has this transition. So this can be done again analytically, but can someone calculate NS power? It's possible, but I think maybe we should push harder to do it. But anyway, at least you see something here. Let's see. I think I need maybe 5 more minutes. Is that okay, Ruben, or is it? Am I?
Yeah, that sounds perfect.
Okay, maybe 6, but it's something like that. So now, what about area of subsystem negativity in a state time evolved with chaotic Hamiltonian? Earlier I mentioned that both eigenstates and time evolved states for chaotic Hamiltonian have this transition from area law to volume law. Can you see that from some analytical argument? So that was actually much more fun in some sense, because you have to actually prove something before that. You have to prove that you have to find the given to density matrix rho and omega, if they are close by in some one norm, like they look similar. Can you first have to prove that their negativity looks similar? Because I don't know, it turned out very useful, these kind of things. And it's so you can prove what's called continuity of negativity, if how close a negativity must be if the two states are nearby in terms of Hilbert space dimension and the two norm of their difference. Okay, so you do that. How does it help? So so consider now an initial state, which is superposition of eigenstate. M is the eigenstate, and then use this for rho. So there's an inequality here. For rho, just use your target state, which is density matrix over A union B, which is obtained by tracing over C. For omega, you used trace over C of the following density matrix, which is called the diagonal density matrix or diagonal ensemble. Integrate a rho over all times, average. So it basically it has the sum of projectors onto eigenstates. And using this inequality, which we proved, you can show that you can show that the negativity of the long time state and this average state is basically same. And the average state using subsystem ETH has a area negativity up to when VAB is less than V over 2. So anyway, so this was the proof, and you can details again. You have to see the paper. It's again, it's a technical thing, but it's not that hard. It's just, I don't know, just 3 or 4 times you use triangle inequality. So the final part, which is just last few slides, is okay. We have developed now some intuition for negativity when it's area law, when it's volume law, and so on. Can we use it for something good beyond just standard things like chaotic and integrable and all this MBL states? So there is this very kind of maybe somewhat controversial thing, which we call quantum decentralized with Matthew Fisher, which is that we propose that they may exist. I forgot a citation, sorry, this is work with Matthew Fisher several years ago. We propose there may exist eigenstates of some in a two-component system, which take the following form: that you write down the many-body eigenstate in the sphere is a product of two terms. This is a caricature state. So let me call capital R the heavy particle, little r the light particles. It looks like this form, a product form. There's a part which is only coming from heavy particles. And then there's a part which has a index R, which is for each fixed capital R, each fixed location of heavy particles, this state phi is actually area law. So that was our kind of that's what we had in mind for this proposed, at that point, unknown Hamiltonian. And it had a lot of good features. So the idea is you measure heavy particles. When you measure heavy particles, this psi part goes away because they're just numbers. Capital R's are now numbers after measurement. But the light particles are still dynamical. They are quantum variables. And after measurement, you have completely disentangled the state. That's why we call it quantum disentangled liquid. At that point, we did not know how to find its states. But later, there was a very nice work by Jim Garrison, Ryan Mishmash, and Matthew Fisher, where they found actually Hamiltonian which has these states. And now I think it's much more believed that based on Bethe ansatz also, for at least integrable Hubbard model, you can find such states. So there's more confidence they exist. So they consider this model, this work by Garrison and collaborators, some extended Hubbard model, and they found evidence of these states, where the light particles are like charge, heavy particles are like spin. So for example, if you measure all the spins and let charge fluctuate, then entanglement of even finite energy density states is area law. If you do other way around, it's volume law. So this was the evidence they provided, but the key column in this whole thing is this lower right. So when you measure spin and look at a charge degree of freedom, they become area law, because spin is the heavy particle. And these are all finite energy density states, which have volume law and entanglement in the usual sense. Okay, that's interesting. So doing this diagnosis require a lot of measurements and averaging. It's much like this recent work on all this hybrid circuits. You have to do a lot of, lot of sampling. Is there something else you can do? So, so this is work with John McGreevy and Daniel Banzine. So the key property of this quantum disentangled liquid, that the reduced density matrix of light particles can be written as a sum of several density matrices, all of which are shortly entangled. That actually just follows from the wave function I wrote down. You can derive this result. So think of light particles forming region A and B, heavy particles forming region C. Irrespective of how large the Hilbert space of C is, this decomposition always holds because of QDL property. So reduced density matrix over A and B is always separable, essentially, between A and B. In a truly chaotic system, that's not true. We already discussed there's a transition. When region C is less than 1/2, then the entanglement between A and B is large. It's volume law. But this suggests it will remain area law for this QDL states, even when C is small. This is a conjecture. So let's test it. So this is the work. So if you take this QDL state, so in the spectrum of this extended Hubbard models, there are exponentially many states which are QDL-like, but they are still exponentially rare compared to the full states. So go to that band, this QDL band, and pick up those states and do this. Look at the negativity when the heavy particles, our Hilbert space is much smaller than or let's say not much more, but yeah, I mean the number of spins of the heavy particles is less than the total number of lighter spins. And you find for the QDL states, it's basically zero. Entanglement is basically, I mean, just area law. But for the chaotic state, it's volume law as we expected based on this diagram I showed you. In fact, when we wrote this paper, we were aware of this transition because of work with my student that were still in preparation at that point, but we still put out this work with McGreevy and just cited the future paper. But anyway, but yeah, a lot of credit goes to my student for actually finding this transition in this other paper. So anyway, so so negativity after tracing out less than 1/2 is this, and so this is a very clear distinction between quantum descending liquid and chaotic systems, because of separability enters in a key way. That was another point I want to emphasize. This notion of separability is very interesting. It's not like some kind of thing which we use all the time, but it kind of gives a lot of insights into even these things. And I'm still learning, and it always kind of, it's always very, sometimes confusing, but it is a very interesting concept. So these are a few future directions. So I think I'm done, but the one question is, are there models where singularity exists only in quantum correlations at finite temperature? Like in this 4D Toric code, there is actually a thermodynamic. Can you find a model where something dramatic happens in entanglement, but nothing else? That is what I will call a truly quantum transition. And we have one example. Again, I don't have time, but it's a very sick example. It involves like a spherical kind of model. It's a many-body example, but it's where we have such an example. So, but anyway, that'll be very cool if you can find more physical examples. And can you use the separation between classical and quantum to speed up DMRG? I would say the Metz algorithm of Steve White is already doing to some extent, but I think one can do much better based on some of these ideas. But we are playing with it again with my student Sung Cheng. And other thing is, what about industrial applications of negativity? That is, if you are given some noisy quantum computer, this is a true measure of entanglement. Perhaps is to optimize your parameters to minimize, for example, quasiparticle poisoning or anything else, to just maximize negativity, because that's what ultimately determines quantum coherence. So, and you can also probably understand fault tolerance transitions in terms of negativity. And another direction is, when you heat a system up, you're kind of letting some particles enter the quasi-particle poisoning setup. Others you're not. If there's a hierarchy of masses for anyons, you can actually, heating can be thought of as anion condensation in terms of mixed entanglement. So you can see interesting transition. Toric code was so simple, it just drops to 0, but if there are many, many quasi-particles, especially it's a non-abelian system, heating up little bit, I mean, by little bit, I mean like it should go to 0 temperature in thermodynamic limit, but it can keep it as a function of some length scale like 1/L. You should see several plateaus in negativity, and which are very much like anion condensation. And then understanding more general scarce states using negativity, that's clearly open. And what about other measures? There are many other measures of mixed entanglement. Negativity is the only one which does not require optimization over all possible states. That's why we use it, but maybe one can make some progress for a simpler model like Toric code. So, all right. So I think that was it. Sorry, maybe I crammed too much here, but so any questions, I'll be very happy to discuss.
Tarun, yeah, thank you very much for a very interesting talk. Given time, let me just officially close the meeting here and recording, and then anyone interested with questions, just stick around. And